I'm Rob Richardson. Let's dig into databases in the microservices world. Here's the part where I tell you I am definitely going to post the slides on my site tonight. Well, I've been that guy chasing the speaker, so I can tell you they are online right now. Hit up robrich.org, click on Presentations here at the top, and you can scroll down to Databases in the Microservices World. The slides are online right now. While you're here at robrich.org, click on About Me and you'll see some of the things that I've done recently. I'm a Microsoft MVP, a friend of Redgate, a SingleStore developer evangelist, and AZ GiveCamp is really fun. AZ GiveCamp brings volunteer developers together with charities to build free software. We start building software Friday after work. Sunday afternoon, we deliver that completed software to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp. Or if you'd like a GiveCamp here or wherever you're connecting from, hit me up on Twitter at rob_rich or by email, and let's get a GiveCamp installed in your neighborhood as well. Some of the other things that I've done, databases, SQL source control basics, that was a lot of fun. Mine is chapter 8. And one of the things I'm particularly proud of, I replied to a .NET Rocks podcast episode. They read my comment on the air. They sent me a mug. Woohoo! So there's my claim to fame, my coveted .NET Rocks mug. So let's dig into databases in the microservices world. What do we need to be able to do databases in microservices? We talked about this guy. Well, let's first take a step back and look at applications with microservices. I love this evolution where we started with spaghetti, we moved to lasagna, an N-tier architecture, and now we're at ravioli, microservices. Such a cool analogy. Here on the left, we have a monolith. On the right, we have microservices. Well, why did we use a monolith back in the day? Well, probably because deployment was hard. We got to the point where we really didn't want to do it, so we didn't do it very often. And, well, once we deployed, we'd probably spend all weekend getting it to work again. Deployment became much easier, and so it was fun to deploy into smaller pieces. Now we have lots of microservices. Now here on the right, we have each of the microservices, and that allows us to iterate on pieces of the software without having to replace the entirety of the software. That's great. Yet, one of the major tenets here of microservices is that each microservice should own its own database. Here's a microservice and its data. Here's a microservice and its data. If this microservice wants to get to this data, it calls into this microservice to do so. Microservices. Each microservice does one small job. It's easy to replace these microservices without replacing the rest of the application. Maybe we're just doing a version upgrade, or maybe we're completely replacing it with a new business goal. We can scale each of these microservices independently to be able to optimize our hardware use. And they're easy to replace. And the critical piece, they own their own data. Now the beauty there is that, well, we don't need to go check with all of the other teams in our organization to understand if this column is being used. We can just look through the source code of that particular microservice. If that service isn't using that data, the data is unused. Yet usually when we move towards microservices, we end up with something like this. We have all of these microservices, but they're all communicating with one big monolithic database. Now, why do we get here? Well, because the DBA said no? Well, what are the goals of the DBA and the developer? Well, the developer wants to be able to deliver value to customers by adding new features. The DBA wants to deliver value to customers by maintaining uptime. We're both delivering value to customers. And so, how do we work together to deliver quickly and efficiently and maintain uptime? If we get on the same side of that problem, we can solve this in a much more elegant way. Well, probably the reason the DBA said no, outside of I just don't want to do it, is deploying databases is hard. Have you ever tried to install SQL Server as a developer? Or have you ever tried to install Visual Studio as a DBA? These are hard. We need automation in place to be able to provision databases, to enroll them in backup and authentication mechanisms and ensure that our database is, well, provisioned correctly. We need some automation to be able to do that. I've been that guy where we say, yeah, this microservices database is getting corrupt. Let's restore it from backup. We did back it up, right? Right? Those are some really uncomfortable conversations. So if we must use a monolithic database, maybe we're coming from a brownfield project, or maybe we're new to microservices, we can create a bounded context. A bounded context is that portion of the data relevant to this particular task. Let's look at two examples, a shopping cart and a fulfillment service. In a shopping cart, we need, well, the product catalog. We need all of the products in all of their descriptions. We need all of the product images. We need, well, we don't need read and write access to it. We only need read-only access to the product catalog. But we do need the ability to create orders. So we'll have a bounded context around a read-only view of the product catalog and a create mechanism into orders. By comparison, a fulfillment service, they don't really need the product catalog. The fulfillment service needs to be able to reconcile the product key to a product code, understand the capacity in the warehouse and how much is available, but that's it. For the most part, they're updating product quantities and they're updating order statuses. That's it. So let's draw a separate bounded context around updating order status and updating warehouse product quantities. These two bounded contexts don't need to overlap because, well, they solve different problems. That's perfect. At the point where we do have enough automation and automation around provisioning databases, enrolling them in authentication and backup strategies, then we can move to, and I'll coin the term here, microdatabases. Microdatabases are really elegant. It's the database owned by a particular microservice. Here's microdatabases. Each microservice may have one or more microdatabases that accomplish the task for that particular microservice. Now, each microservice, each microdatabase is specific to that microservice and automatically enrolled in backup, authentication, and provisioning mechanisms based on the automation that we have in place. Well, what's interesting is now we have lots of little databases. These databases don't all have to be the same kind of thing. A microdatabase. It's owned by one microservice. Other services call this microservice to be able to get at the data in this microdatabase. And once again, what's really elegant here is that, well, if a column is unused by the microservice, the data is unnecessary in that microdatabase. We don't need to go query all of the other teams and see who's using this. Microdatabases. As we start getting into microdatabases, we might hit a few challenges. How do we do joins, for example? Do we really have to call that other service, passing in each of the IDs? If I'm going to join on this table, do I really need to call that service 71 times for each of the 71 rows in my report? Let's look at a different strategy. In our order example, the shopping cart service could publish events to the enterprise service bus. Those events could be order created. Now, as the publisher, it doesn't need to worry about who's listening to those events. It can just publish the order was created. Now maybe we have a billing service that listens for that order created event and charges the user's credit card. The billing service can publish a new event saying order was billed. Now the fulfillment service can listen to that build message and start the process of filling the boxes and shipping the content. We can see how each of those services can start to listen to the data that it needs and do the task that it needs to. Maybe we'll have another report service that listens to all of these things and starts to collect order metrics. How long did it take from order creation time to fulfillment time? How often did the credit card processing fail? These are things that the order processing service needs to keep track of, or the order report service needs to get track of, but the order processing systems do not. So that report service now has access to all the information by listening to all these events. And when it comes time to run the report, it doesn't need to join on other microservices data anymore. It listened to the data coming out of the event source. Here's another concern. Who owns the customer record? Is it the shopping cart? Well, the shopping cart is going to create new orders, so they definitely need to know who the customer is. How about billing? They probably have sensitive information hooked to a customer, like the credit card numbers. Or HR. HR is full of secrets. They need to make sure that only their secrets are maintained in their bulkhead. And sales. That's probably where customers start. But sales has interesting concerns. A lead or a prospect is very different than a customer. A customer has a shipping address, maybe a credit card on file. A lead is, well, maybe just their name and phone number that they wrote on the back of a napkin. So should sales be responsible for creating customers? Instead, let's create a new microservice, a customer microservice. Now here in this customer record, we may only have two fields, the primary key and the account number. Whenever any other service needs to get access to this, they can call in and say, hey, I need a new account number. Here's my account number. The customer service can validate that it's unique and hand back the primary key. Or help me resolve this account number into a primary key. It takes the account number and returns the primary key. Now, at that point, this customer service, this customer record, is really narrow. Now, the shopping cart can have a customer profile that may include their recent purchases or their shipping address. The billing service can have another customer profile that includes their billing details, their credit card details. HR can have their secrets inside their customer profile. Now, there isn't one big customer profile record. There isn't even one big customer record. Each of these systems is able to create a profile that has a foreign key off to the microservice, the micro database in the customer microservice. That's great. Now we've got the micro databases. We had the automation in place to be able to get to these micro databases. We have backups and authentication, and now we can start to dig in. Well, the cool and interesting part is each of these databases don't need to be the same type or same vendor anymore. We can choose the database vendor that best matches the problem that we have. Says me. Right now. Well, let's take a look at each of these database types and explore when we might choose each one. With each of these database types, we'll take a look at the pros and cons and identify scenarios where these are best used. Relational, document, graph, key value, time series. You might have heard of some of these. Search, object, event sourcing, column store, and NewSQL. I suspect NewSQL might be new to you, and that's wonderful. Let's dig in. With each one, we'll understand the characteristics of that database and when we might choose it. Let's start off with relational databases. We can think of this kind of like an Excel spreadsheet. We have rows and columns, and the data in each row is specific to that record. The data in each column is the same type. Maybe we have states in the United States or provinces in the country. Each of the data in that column is going to be a state or a province. The SQL engine is really tuned and has evolved over decades to be really optimized for this task. We also have ACID compliance. Let's take a look and dig into ACID compliance. ACID compliance is a mechanism where we know that the entire process will either succeed or fail. We won't have part of the data in our database. By comparison, we have eventual consistency. If I go into a store and I create a purchase, and then I quickly go check my credit card statement, that purchase may not be there. But by the time my statement comes, I know that it is consistent, that I have my final bill. That is eventually consistent. In a SQL database, we have ACID compliance. It isn't necessarily eventually consistent. It is always consistent. By the time our transaction succeeds, we know that that data is in place. With a relational database, they have been tuned for decades, but they were built in an era where single processors were the thing. So usually you're scaling relational databases vertically. On the upside, we have great tables and schemas. We have great SQL mechanisms. This is a very optimized and familiar experience. On the downside, we may need to, well, migrate that schema from time to time to be able to evolve based on the needs of our application. Ultimately, relational databases were built to optimize data storage. So as we look at third normal form, that's really a mechanism to store data in a small space, which may not be the concern now that we have terabyte and petabyte sized disks. Ultimately, with a relational database, because it scales vertically, we may get to the point where there just isn't a bigger box or we can't afford it. A relational database, here's some examples. Relational database is a good default. If you don't have a database in mind, a relational database is a good choice. Probably if you have a monolithic database, it is a relational database. Next up, let's look at document databases. Now we might think of these as NoSQL, but well, basically everything in this list that isn't relational is NoSQL. So let's call this document databases. Here in document databases, we store, well, JSON objects. Now in a JSON object, we can nest our fields inside of arrays. We can put all of our content inside of this nested object. And so we can fully express the needs of our application in these nested documents. Now we will build them into collections. A collection is, well, in SQL terms, a table. On the upside, a collection can have documents that are different. Maybe we've evolved the schema and added new fields, or maybe we're just storing different types of documents in one collection. Now that's great, but we've sacrificed joins to be able to pull this off. Now document databases were created in the realm of multiple machines, and so they horizontally scale across a cluster really easily. On the upside, we have no schema that we have to worry about. On the downside, we have no schema. And so an application probably has in mind what they expect from the data. And now we need to have in our application error logic around, well, what if the data doesn't look like that? How do we where in a nested field if that field doesn't exist? On the upside, we can store documents in a really elegant mechanism. On the downside, we can't do joins. We can scale horizontally, which is really elegant, but we probably have to have a unique query syntax, a unique SDK per language per database. Now, some document databases kind of pretend that they're SQL-ish, but it's SQL-ish. It's not SQL. Here's some example document databases. Document databases are great because they're optimized for reads. They're great for things like a product catalog, a news site, maybe a CMS. If I'm taking that news site, when I hit that page, I want to be able to grab all of the details for that article. The title, the article content, the author name, maybe the first few contents, the first few comments, all of the pictures associated with it. I want to grab that all in one go. Now that does mean that if I need to rename somebody, I'll need to go through all of their articles and rename them. That's okay. It's optimized for reads, not optimized for writes. Next up, let's look at graph databases. Graph databases focus not only on nodes, but also on relationships between nodes. I can store data in both the objects and their relationships. It's great for social networks. Now, how is this different than, well, say, foreign keys? It's that query syntax, that mechanism of being able to do nested joins on those relationships. On the upside, graph databases are really tuned for being able to do this fast join across these relationships. On the downside, it's tuned for that and not much else. So we may lose out on join performance when working with other tables. Here's some example graph databases. They're great when I want to keep track of relationships, messaging apps, social networks, maybe recommendation engines, when I want to keep track of those relationships between things and hang data off of those relationships. Next up, a key value store. A key value store we can think of as kind of two columns in a database. One is the key and one is the value, which may be different across all the rows. In a key value database, we can, well, deserialize the data coming out of that value however we need to. Maybe we're storing configuration data, and some configuration details are arrays, some of them are comma delimited lists, some of them are single objects, some of them are JSON. We can think of this kind of like, well, two columns, one key and one value. It's great for doing get by ID type of work, but it's really not great if I need to do any where clauses on any other data. If I needed any other data from my where clause, I should break this down into a relational database where I can get at that data more easily. Here's some example key value databases. They're really great for caching or configuration or user session data, places where I just want to get or set by ID. I'm not going to do any wheres on any of the contents of that content. Now, what's beautiful here, especially for caching and configuration, the values don't even need to be the same. If I'm saving my shopping cart data into one value and I'm saving my connection string into another value, that's totally fine. However the application reads that key, it can deserialize that value in the way that makes sense. Next up, let's look at time series databases. Now, time series databases are great in that we have this query language for identifying time. Now, in most relational databases, when we have a row and a column that match in a cell, we have a single value. In a time series database, we have a time window. So now we have multiple values that fit in a cell. Now that we have multiple values in a cell, we can look at min, max, average. Time series databases are great for building candlestick charts. On the upside, we're focusing on time. On the downside, well, we're kind of leaving other things behind. Joining on non-time series tables may be less performant. Here's some example of time series databases. It's great when I'm processing time-focused events, maybe IoT device metrics or mobile device click streams or stock trades, things that are very time-centric. Next up, let's look at text search databases. Text search databases are great for identifying which documents match this phrase or where in this document is this phrase. Now, I might choose to combine a text search database with a natural language processing engine, and then I'll probably get, well, a search engine. It isn't necessary for us to match a time series database with a natural language processing system, but it is common. Pardon me. In a text search database, we have an inverted index. Let's think of this like the index in the back of a book. Let's go through our entire document and count the number of times that we have this particular word, linking back to that spot. Now, when we get to the back of the book, we can look up that particular word and know all of the pages that have that word in it. Text search databases are great for being able to catalog text and find content that is text. On the downside, it's not great if I want to do other types of things. If I want to say filter by all of the content only in a particular region or only specific to a particular domain, I probably need to store that data in a relational database and pre-filter the documents that I'm going to check in my text search database. Another thing that's really difficult here is stop words. In English, a, an, the, of. These words don't have a whole lot of meaning, and we're going to have a lot of instances in our documents. So maybe we'll just ignore these stop words. If we're working in different languages or different cultures or certain domains, then we might have different stop words. We've chosen, if we're looking at geography data, we might choose to add av and road and street into our stop words. So now what if we're in Seattle and we're looking for Avenue A? We've said that av is not a word and A is not a word. Does that mean that we can never find this piece of data? Stop words are very specific to the domain and the language and culture that you're working in. And it's easy to trip over these stop words. Here's some examples of some text search databases. What I find really interesting is that they use indexes differently. Some of them apply them at the point of data ingest and some at the point of query, which is really cool. Next, object or blob stores. We can think of this roughly like a file system. Amazon S3 is a great example. Now, it isn't a file system. We don't actually have folders, but we can put in forward slashes and pretend that they are folders. Now, the value is a big binary blob. Now, this is great for storing large image files, movies, database backups, things where we need cold storage to be able to store a lot of content. We can't easily query by anything but that key, Much like a key value database, we would need to read each value, deserialize it in a way that makes sense, and then query it. Which is the blob where I modified this document last? That's not something an object store can tell us, but let me get the content of that file at this particular date. I can definitely do that in an object store. So I may need a relational database to store that additional metadata. Here's some examples of object stores. It's great for that big thing that you need to get and save by ID, but it's not great at doing where clauses. Next up, event sourcing. We looked at event sourcing a little bit as we looked at ways to overcome joins with microdatabases. I'll have a producer that is writing to the end of this queue, and then I'll have consumers reading off of the front of this queue. Here's one consumer that's up to row 6. Here's a different consumer that's up to row 8. Now the cool part is it creates this asynchronous communication channel where the consumer and the producer don't both have to be online at the same time. The producer can just write data, and when the consumer's ready, it can read it back out. We can filter this based on channels or topics to be able to subscribe to only those details that we need. Event sourcing is great for being able to create asynchronous mechanisms between systems. The publish and the subscribe don't both have to be online at the same time. We can also create mechanisms where if our business rules change, we can reprocess this data using the new rules. On the downside, how do we get to the current version? Well, we play in all of the previous events. We have an eventually consistent system. So we may pair an event sourcing system with another system that keeps track of the current version. Now, which one's right? Yeah, let's choose one system of record, and if ever there's a conflict, that's the one that's right. Here's some examples of event sourcing databases. It's great to be able to asynchronously communicate between systems and to be able to reprocess data if our business rules change. Next up, column stores. Now, what's interesting about a column store that's very different from a relational table is that we store our data in columns instead of rows. On the left, we have a relational system where we have all of our rows. On the right, we have columns. Now let's imagine that we're storing states in the United States or in Canada, or countries in the world. Now there's only a finite number of them, so we can compress this data a lot. Once we seek down to that state or province that we need, we can quickly read all of the data associated with that. Column stores are great for analytics because we can quickly scan through data and quickly bulk read data. On the downside, it's not great for transactional systems where we need to do random reads and writes. A column store is great for analytics, OLAP workloads, not great for transactional systems, OLTP workloads. Here's some examples of some column stores. Next up, NewSQL Databases. Now you might not have seen this before. This is really cool. A NewSQL database marries the SQL engine, ACID compliance, with a distributed system, like we'd see in a document database. Our data is sharded across different partitions, and then we can receive a query through an aggregator that can enroll whichever leaves that we need to get the data, and then we can gather the data for the result set, and the aggregator can collect it and turn it into a deterministic result. This is really cool because now that we've split this up into multiple machines, we have the ability to add commodity hardware to be able to expand our system beyond its current capacity. We don't need a bigger box. We need more regular boxes. That's great. On the upside, we have a really elegant way to scale our system horizontally, where we didn't in SQL systems. On the downside, there may be some network activity. Let's say, for example, we need to join the data from this partition with the data from this partition. So we may have some network activity as we move the data across nodes. Now that's okay. Ideally, they are really close both physically and on the network to ensure that they have really fast access between each. But yeah, we do have a little bit more complexity and we need to pick a good shard key. Here's some example of NewSQL databases. It's great when your SQL database has kind of capped out its capacity, when you're tired of that spinning wheel. You can go to a NewSQL database and you can start to scale horizontally where you couldn't in previous SQL databases. Ultimately, we may reach for a hybrid database. Maybe it's a SQL database, but it has a JSON column to be able to do NoSQL queries as well. Or maybe it's a SQL database, but it also has time bucketing. Maybe it's a NoSQL database, but it also does key value data. A hybrid database is, well, yes, and a lot of databases are going in this direction. Here's that money shot. Grab your camera or grab these slides from robrich.org. Here's each of the types of databases that we looked at, what they're best for, and when you might choose it. We looked also at architectures, monolithic databases, and microservices. If we are stuck with a monolithic database, let's use bounded context to be able to identify the specific data, practice separating our data into small pieces. Once we have the automation for backup and authentication and provisioning, then we can get to that spot where we have micro databases. Here's all the different types of databases that we saw. And what's really cool, we can choose the database type that is best for our application. If it's not a great fit, a relational database is a good default choice. My recommendations: start with database as a service. Let somebody else manage uptime and point-in-time restore. Those are things that I don't want to have to worry about anymore. If you have automation, then you can get to micro databases. Choose a SQL database by default. ACID compliance is really handy, and SQL is a pretty well understood and optimized query syntax. Choose others if you have a perfect match for that type of database, or see if your SQL database is hybrid in the ways that are important to you. Ultimately, when you move towards microdatabases, you can choose the database type that is specifically tuned to the needs that you have. This was a lot of fun getting to present databases in the microservices world. Join me in that spot that the conference has designated for Q&A. And if you're watching this later, hit me up on Twitter at @rob_rich, or grab these slides from robrich.org and let's continue the conversation. Thanks for watching.